Hi, my name is Larissa Svitsky. I will be presenting on our paper towards automated DNS tampering detection using machine learning. So first, why does this even matter? DNS censorship, domain name systems, play a crucial role in internet freedom, internet communication by mapping the domain name to IP addresses for routing traffic. However, DNS is vulnerable to manipulation when it comes to DNS responses that are tampered with. So DNS manipulation can be done on multiple levels through rogue resolvers or injections. For example, manipulations can cause redirection to block pages, malicious sites, lookalikes, or no responses at all. It is also really easy to manipulate, which is why it has become one of the most common blocking techniques. So current efforts to detect DNS censorship manipulation have mainly relied on heuristic-based approaches. Usually it relies on IP consistency checks between the DNS responses at the testing and the control site. Rule-based heuristics are not fully accurate, though, and legitimate discrepancies in evolving censorship techniques often lead to false positives. For example, with CDNs and dynamic IP address allocations are often marked as false positives. Other challenges include evolving blocking signatures, outdated hard-coded rules, variations by countries, vantage points, and time. So to try to figure out how to detect DNS censorship, there is machine learning as an emerging approach. As heuristic analysis falls short, machine learning offers two key benefits. It excels at analyzing vast amounts of data to identify patterns that might not be apparent to the human eye, and it has an ability to scale. As the volume of data grows, machine learning models can be trained to handle more complex and larger data sets. So our motivations and contributions. Our motivations for this paper were to find a better way than insufficient traditional rule-based heuristics. We aim to combine traditional approaches with machine learning to tackle the lack of ground truth and insufficient results from heuristic-based models. Our contributions test the extent to which ML is valid and applicable, including assessing models' temporal generalization. We also conduct our study on a global scale, where most papers have been focusing on doing it by one single country. And we widen the scope of control by offering widening the scope of the control for using ASN matching rather than IP control. So to start with the pipeline that we made, we did data collection, pre-processing, and cleaning on our first step. So our curated data set encompasses 2 years or 24 months of UNI data from January 2022 to December 2023. And rather than only having one country, we used all of the available countries and measurements that UNI has. So to get into some of our pre-cleaning, because we need to do that in order to make sure our data set doesn't have any wrong data to mess with our training. We have to first fill in missing data. Our model uses ASN control rather than IP control. However, all UNI records did not contain this since it was implemented later. We used a combination of two sources to map the IPs to the ASNs, and one was for the historical, one was more current, just to try to make sure that we had valid data. And if we were unable to find that data, then we would drop the measurements so we wouldn't have any, we would ensure the quality of our training data. Oh, well, these are supposed to be the initial fields that we trained on. They usually can be read. So we need to make sure that they exist in order for our model to actually be trained on. They include resolver ASN, probe ASN. There was also body proportion matching and a few other ones. Status code match as well, and header match. So our derived feature for this one that was not from UNI measurements was the ASN control match, which offered the looser interpretation of whether the ASNs differ between the control and testing site rather than using the IP control match, which UNI had already. So now my other co-author will explain some of the machine learning, hopefully. The processes, since there's technical difficulties. All right. The machine learning pre-processing, that mainly consisted of 3 steps: data reformatting and normalization. So they had categorical variable handling and ASN encoding. We reformat the dates to numerical formats representing the days since a particular date. And we had continuous variables on the other hand, which were normalized, ensuring that the variables contribute equally to the model. With categorical variables, we created a dictionary that maps each category to a numerical value, and then used this key to perform one-hot encoding. One-hot encoding transforms the categorical variables into binary vectors. The ASNs are directly one-hot encoded in order to preserve the structural information in the ASNs. And we had splitting data. So once we have our encoded data, we have to split it into 3 different data sets in order to do machine learning. We had our training, validation, and tests. The training set contained the bulk of the data at 80%. This data set is used to teach the machine learning models. At this phase, the model learns patterns and relationships within the data. The validation set consists of 10% of the data. This purpose was to tune the hyperparameters of the model. The hyperparameters are settings that can be adjusted to optimize the model's performance. By using separate validation sets, we can evaluate different configurations and select the best one without overfitting the training data. And finally, we have our testing set, which is 10% of the data. Once the model is trained and tuned, the test set provides a theoretically unbiased assessment of how well the model generalizes to new and unseen data. So some of the terms that we have to discuss for machine learning are clean data, which is not marked as DNS tampering and is consistent with the control node. This is, since there's a lack of ground truth, there is a little bit of uncertainty there, but we used the label for UNI to establish that for now. And next we have anomalous data. This type of data is marked by DNS blocked, indicating that UNI has flagged it as containing irregularities or potential issues. So we did supervised models and unsupervised models. For unsupervised models, they are trained on our normal data or clean, and the goal is to teach the model to identify patterns and structures in the data without any labels. Whereas supervised models are trained using both clean and anomalous. By providing labeled data, the supervised model learns to classify data into predefined categories. Then we have to evaluate the model performance. And we do so by computing the accuracy score, default positive rate, negative rate, and so forth. The models that we used for supervised were XGBoost. XGBoost is a powerful gradient boosting algorithm known for its efficiency and accuracy. which we did not base most of our responses on because of the lack of ground truth and having to use UNI data to actually train the model. The unsupervised models, we did isolated random forests, IF, and one class support vector machine, so OCSVM. So for metrics, using UNI data as the ground truth, even though we know that there is a lack of certain ground truth, we can evaluate the metrics. IF has a high true positive rate, indicating it has a correctly identifying the positive cases. However, it also has a higher false positive rate compared to other models. OCSVM has a very low false negative rate, meaning it rarely misses positive cases. However, its false positive rate is extremely high, indicating many false alarms, which signify lower accuracy. XGBoost shows excellent performance because it's trained as you go, with a low false positive rate and a high true negative rate. So we did this all on that we trained models that perform highly at a global scale. And all in all, while metrics are important, without true ground truth, it is challenging to evaluate the model's performance without human expert verification. So for our feature importance, we calculated feature importance using SHAP values. The ASN control match field performed very well on both IF and XGBoost. One of them was at the second highest and the other was at the fourth highest. The other ones that were performed well were the resolver ASN, probe ASN, and body proportion. So another thing that we ran to figure out testing was the temporal generalization to see how much data is necessary for machine learning. The temporal generalization refers to the ability of a model to maintain its performance over time. And we created different graphs to show the performance of the 24 months. I wish I could show you, but it is on the paper. Well, the isolated forest model shows variability in the false negative rate and initial high positive rate. Its accuracy remains relatively stable over time. But the most optimal amount of data was 2 months, so we have found. XGBoost model shows consistent improvement in false negative rates and false positive rates, with accuracy remaining stable and high over time, which was not our main focus because of the type of model it was. So next, we go back to our slides. We have our pipeline, our signature discoveries. So before we handled the splitting data sets, trained models, evaluating the performance, and the feature selection with the machine learning. And now we get to work on the results and our signature analysis. So we can't just look at our machine learning data since there is a lack of ground truth. So we use a hybrid approach. After we did our machine learning, now we are going to look, we developed a methodology to take our best models, and then we utilize majority rules to determine the most agreements for the classification. This is complemented using the model's performance scores. So then we have a label of what we believe would be marked as anomalous or not anomalous. And then we also filter by the agreement of both UNI and our majority rule results containing a high competency score to examine measurements classified by those censored cases. To further mitigate potential false positives called by legitimate discrepancies, we exclude measurements without 50 similar cases. We ran the threshold a few times just to see what would be the best, and we found 50 would be a good number, giving us a higher likelihood of true positive results. So our signature discovery, we found several that were already discovered by the rule set and were pre-existing, so they supported what we have already known. But through the filtering scopes that we implemented on the machine learning that we just talked about, we were also able to discover new fingerprints that were not previously identified by UNI's existing rule set, thereby finding new fingerprint patterns to contribute to the community. This table shows a list of unknown fingerprints identified by OCSVM and IF models. These new signatures could help enhance the existing rule set of known blocking signatures and also further support ones that are already known because they have found multiple that were already existing. So our overall contributions in this paper, we demonstrated that machine learning's power to detect global DNS tampering, and we achieved high accuracy by learning expert-defined heuristics. We uncovered new censorship instances missed by rule-based approaches through a hybrid detection model. And we showcase insights into models' temporal generalization, finding that 2 months of data is enough to train your machine learning model on. And we developed a publicly available pipeline that can be accessed through this QR and our paper. Thank you.
Thanks, Larissa, and thank you for working through the technical issues too. I think we have time for 1 or 2 questions.
Well, first of all, thank you so much for working with our data, and it's really interesting to see people apply machine learning to it. First, I just would like to say we should talk more later. We have also been exploring some of these machine learning-based approaches, and I think one thing that you might want to consider, if you hadn't considered already, is doing some kind of feature pruning to exclude some of the features that are more sensible to overfitting. Like you mentioned how the resolver ASN and the probe ASN represented important features. It might be that the model is learning more about where there's censorship than how censorship is happening. And on the other hand, what was the second thing? Yeah, for the ground truth, what we found to be helpful to build the ground truth is that Russia, which has a very diverse set of networks, publishes their official block lists. So in a way, you can consider that kind of a ground truth because the government itself is telling you what should be blocked. And so you can sort of, and there are also many more official block lists that you can consider as ground truths, and that's what we were using for evaluating all of, because the UNI labels, as you say, are not really that good, you know? Like, we don't see all the things because we depend on people telling us what are the fingerprints. And your fingerprints already filed an issue, we're gonna add them. So anyways, thank you for your work. We should speak more and, you know, keep up the good work.
For the resolver and the probe ASN, we did try to test it without, and we found when we analyzed it, when we've had the probe network name and the resolver network name, it was prone to overfitting, but for some reason with the resolver, ASN, and probe, it was a little bit better with performance. I know my co-author could elaborate a bit more on that.